Welcome those of you who are online, and welcome to all those who are here today in the room. For those of you who don't know me, my name is Phil Withers. I'm a Regents Professor of Materials here in Manchester and also connected with the Royce Institute, and was a long time ago the founding ICAM director. So it's especially good to be here today and to be able to represent all three major activities. We're lucky today to have Professor John Lambros from Urbana-Champaign. Urbana-Champaign is one of the 4 universities that are contributing to the BP ICAM, and so it's great that you can get today. Okay, so just wanted to say a few words about Professor John Lambros. He studied at Imperial College, so another BP ICAM partner. That's for your undergraduate?
Undergraduate, yeah.
Undergraduate. And has subsequently studied at a number of other institutions, including Delaware, is that right?
No, I studied at Caltech. I did my master's and PhD. Delaware was I started working. My first work experience as an assistant professor.
So, is really understanding the behavior of materials under a range of demanding environments, which is another very fitting alignment with the Royce, because one of the research areas within the Royce Institute is materials for demanding environments. So it's particularly opposite that we should talk about. Heavily involved in a whole range of engineering materials and in the use of the study of their behaviors and characterizing their performance and the relationship between their microstructure and performance. And so without saying any more, I'll pass over to John, and thank you very much.
Thank you. No, I have a, yeah, I have a lapel. Right. Thank you. Thanks very much for the introduction. Yes, I saw up there, it said, hold your questions till the end, but if they're really pressing and you can't hold them to the end, I'll be happy to answer them halfway through. So feel free to interrupt. I don't have a problem. Yes, I will use that. Thank you. And is this water is for drinking, or is it for decorative? Okay. It's not there from the previous seminar, right? Okay. All right. Well, it's a great pleasure to be here, and I appreciate the invitation and hosting me. I have not been to Manchester before. I've worked closely with folks at Liverpool. That's about as close as I've come. So it was actually quite nice, having a lightning tour, right, going around the facilities with Phil, and fantastic. Let me, let's see if this works. Yes, it works. Right. So let me kind of introduce the topic of what I'm going to be talking about today by saying that it's not one particular project, right, that we are focused on and studied in detail. What I'm going to talk about today are results that span probably 10, 15 years of effort, and it's kind of my sort of collective thinking of the subject. So I'm not going to go into one in depth in any one particular project, but I'll kind of try and pull a lot of the things that we've done together. It wasn't actually planned this way, right? It kind of evolved. But this is a series of projects that has dealt with microscale and really multi-scale characterization of damage in materials. And we've worked with a lot of materials, but what I'm going to talk about today is essentially metals. Most of the experimental work has been done over quite a number of time, as I said, 10, 15 years. But I'll also talk about some of the more recent things that we're doing, which is the machine learning based model. This is a project, these are mainly projects, a series of projects, I should say, that have been funded by the Air Force in part, and in part by the Department of Energy. And really, I should be pointing here. And before I begin, I really have to acknowledge, and if I leave this at the end, I usually forget or run out of time. Please stop me when I get the time, right? I don't know how much time I have. Because I could just go on for a very long time. And there's certainly plenty of slides. So I put it up front. I have to really thank the people that did the work, which are the students, primarily Renato Vieira, Wael Abuzaid, both of whom are now faculty in their home countries, one in Brazil and one in UAE, and a current student, William No, who is mainly the person that has worked mostly on the machine learning modeling. And I have to thank my colleagues who have been sort of an integral part of this. Hussein Sahitoglu from mechanical engineering and Professor Chu from the Aerospace engineering department, which is also my home department. The two projects are fairly different from each other, but they also have some commonality. The one funded primarily by the Air Force over here, dealt with essentially understanding thermoacoustic fatigue in a variety of different materials, mainly metals, but some additive manufactured metals as well. Thermoacoustic fatigue would be, really fairly elevated temperatures above 1000 C and at very high frequencies, again, above 1000 Hertz. Things that are really typically associated with space reentry or sustained hypersonic flight or things like that, right? So clearly extreme environments of interest to the aerospace industry. On the, what happened? Oh, volume. On the DOE side, the situation that we looked at was a little bit different. DOE had this particular interest for a particular material, a stainless steel material for this secondary heat exchanger in this sodium fast reactor. And here again, we have a situation where both temperature and mechanical loading are present, although a bit different than in the thermoacoustic case. Here, temperatures were around the order of 600-700 degrees C, but timescales were much, much longer. So the sort of the commonality in both these problems is that they essentially both have coupled thermomechanical effects, although the temperature scales and the time scales vary. However, we employ similar tools to study both, and I'm going to present results again from both. As I said, I'm not going to go into details. I'm not going to dive deep into each one of these, but I'll kind of show you how they connect with each other. The work that we do essentially spells, I talk about microscale in the title, but really it's more like multi-scale spans various scales, and multi-scale means different things to different people. So in this context, let me tell you kind of what I'm thinking about in terms of multi-scale, right? So what I think of as a macro scale is let's say laboratory coupon, something like a tensile coupon here, which would give you, just a stress strain curve of what you would imagine would be a homogeneous response. And, for others, macro scale might be sort of even larger. So we do a lot of collaborative work with Professor Patterson at Liverpool, where he continues this kind of one scale up and looks at larger panels and how they would deform. So for me, this is what I would kind of think of as macro scale, something that there is sort of this uniform or homogenized response. Of course, if you look closely, as we all know, there are inhomogeneities at the micro scale. And here's what I think of as well. Let me animate one more. So what I would think of as microscale is, let's say, a grain level scale, which in the materials that I'm going to deal with today is typically of the order of 10 microns, tens of microns perhaps, right? And in between is what I think of as mesoscale, would be a scale in which the collective response of many grains becomes important. And we see this happening, and existing people have studied this for quite some time, right? And we see various patterns developing. You can kind of almost see it here, right? These bands of strain. So mesoscale itself, and this is one of the most difficult areas to analyze, right? People have done a lot of work on all this sort of multi-scale variation, where we start from trying to analyze what happens at this level, and then try and kind of move upwards to what this would look like at the macro scale. There's been a lot of numerical results, for example, that do this, most often through some type of, let's say, homogenization technique, where you kind of try an average of something over something you would consider, a representative volume element or an RV. This in itself there's a question mark there. We've done a lot of work, both experimental and numerical, on what really is an RV and what it constitutes. Again, I'm not going to talk at all about that here. But what I'm most interested here and what I'm kind of going to focus on is, well, how does failure occur at this scale? Well, at the meso and in the micro scale, right? So these local effects, which of course ultimately, certainly in terms of design and use, are really one of the key questions that we want to answer, right? Because you could have these small local effects that would happen at this scale that can definitely affect the macro scale and cause catastrophic failure, right? So this would be the thing that we would want to avoid. So these are kind of the scales that I'm going to talk about. So mainly these two scales are what I'm going to talk about today, although I'll show some macro scale results as well. This multi-scale analysis that we will do experimentally, we'll do with high resolution digital image correlation. I'm sure most of you are familiar with this. I'll kind of go through quickly kind of exactly how we do this. And then I'll show you some experimental results from the two main topics that we've been interested in, the thermoacoustic fatigue on one side, and then creep fatigue on the other side. I'm also going to show some cyclic plasticity experiments. This is kind of the starting point, what we kind of started off on. And then after these experimental results, what I'm going to show you is some models that we try to do to obtain these types of results through now a machine learning framework. There's been a lot of deterministic modeling in this area as well. And then lastly, if you have time, kind of the most recent thing that we're interested in. So this type of modeling essentially would be trying to follow the idea of, well, given a microstructure, can we predict strains and eventually failure, right? So just looking at the microstructure, can we tell where, when also something would fail, right? And here is kind of what I think of as the inverse problem. Given a strain field, can we say which microstructure produced it? And that's one of the things that we worked on most recently. The short answer is yes, actually, quite a lot better than anything that I thought would be possible. So anyway, as I said, we use multi-scale digital image correlation. You're all familiar with this, I presume, so I'm not going to go through the details, just a pattern, random pattern, image before and after, and that allows us to obtain displacements, displacement gradients, and so on. And this is, I always like to show this. This is a process that we do by eye very quickly, right? So if I just snap through these two, you know, what is this, right? You can kind of see. It's just a rotation. The whole thing is just rotating, right? And indeed, that's what DIC would give you. But even by eye, we can do this fairly quickly, right? With these types of sort of simple deformations. So yeah, we could use this at a macro scale. So we can think of this as a tension, a uniaxial tension specimen. This would be sort of the subset where the DIC would occur, right? So essentially, it's if you think of the underlying microstructure, it would essentially be averaging a large number of grains. So you would have something like maybe something that would look like this, right? So this subset would again give you an average response. If you want to achieve subgrain level resolution, of course, you need smaller subsets, which means zooming in, which essentially means having to put this under a microscope, and that's exactly what we do. And then, you know, similar to some of the techniques that I saw here, well, the penalty you pay for this is a field of view. So essentially, we do some kind of rastering, and then we stitch everything together to get sort of mega images, as I call them, 140, we've done 200 megapixels and so on, right? So you have very, very large. Now, with the newer cameras that now have, we used to do this with 1,000 by 1,000 cameras, we might take 100, 150 pictures, very labor intensive for the graduate students. Again, 10 years ago or so. Now this is automated, plus we have higher resolution cameras. So we can do this with fewer cameras, but the downside in some sense, let's say, is that this I think of as the ex situ, right? So things have to be stationary, not moving. So it's more difficult to do this in situ. And I'll show you some of these in situ versus ex situ results in a sec. This would be a typical setup for the thermal and mechanical experiments. Again, for metals, most of the heating would be through induction heating, and it's a bit bright here, right? So this is kind of a close-up of the sample over here. These are the induction coils. This is a little spot from the IR laser to monitor the temperature. And then the DIC camera is on the front. That would image the pattern. When the induction coils are on, here's what this looks like. This is a specimen going away. You can take it to melting if you wanted to. These would be the type of measurements that we've done. And again, we've done a lot of experiments in various configurations, in various situations. But here thinking of a fatigue experiment, right, where you have some kind of cycling. You can take images and analyze them within a cycle. So what I think of sort of as in situ, and this would give you the effect of increase and decrease of loading. So you would correlate these green dots with this blue undeformed image, and you would get something like, for a crack, for example, you might get this typical plastic zone here that you would see on the lower left there. Or you can correlate between cycles, either in situ or ex situ. So between cycles means, let's say that you go to the same point, let's say the bottom point of the fatigue cycle each time, and you correlate with some initial image, and you can do this with whatever frequency you want. I say 100 cycles here, but whatever you want. So essentially, if there were no change here between these points, meaning that there was no damage accumulation over time, these would just provide no correlation. But they don't. They actually provide some type of result, as is shown up here. And essentially, what you're seeing here is the plastic wake, right? So this is the plastic wake of a fatigue crack. There's been some load shedding that happened here, which is why it gets interrupted. So this would be a in situ experiment between cycles, but we could also remove it or not remove it. I guess doesn't matter. We have moved sometimes the microscope up to the machine, and then do this rastering and getting this sort of mega pixel image and doing the higher resolution imaging and getting again what would be fatigue. It's not exactly the same, right? But this is actually in a different material. But what we would be getting would be a higher resolution of this plastic wake, right? Or we could get a higher resolution of the development, the plastic zone in front of the crack tip. And you could do this at various magnifications. And then we could also do eventually a monotonic test of failure to get, let's say, stress fracture toughness or whatever else, right, that we might want. So these are the types of measurements that we would do. We want to correlate these eventually with microstructure, which we will do through correlating with EBST, and we want to align this with the DIC data set, and that's what these markers are for, to help in the alignment. And we also use in between this optical grain boundary image to kind of help also again with the alignment and with any grain boundaries that may be missing from EBSD or from optical. Ultimately, what we have is a combination of strain field at this mesoscale, which again would be this sort of collective response of the grains, along with grain boundaries and then grain boundary orientations. Everything on the surface, of course. What I'm going to talk about here, everything has been on the surface. We've done some 3D studies, but I'm not going to talk about that today. So some results, typical results. First, let me start with cyclic plasticity. This is kind of, understanding cyclic plasticity is really almost essentially a precursor to understanding fatigue, because essentially fatigue really is an outcome of plastic irreversibility. If everything went back to where it started from, every cycle, there would be no fatigue. So essentially what we do here is a series of loading, unloading experiments on a particular material. Again, this was in terms of the Air Force funded project. So it was a nickel superalloy, Hastelloy X, that we were looking at. And essentially we would correlate using this high resolution technique, we would correlate residual stresses between certain points, the ones that are highlighted. So if we look at what happens between, so what this mesoscale strain field looks like between 2 and 4, roughly 4%, you would get this. This is just uniaxial tension. So this is the dominant strain component. You have all of them, of course. Right, so essentially you see, yes, indeed, a highly homogeneous field. Some of it is compressive, right? So the dark blue parts are compressive. And you can try and correlate this with grain boundaries and so on. And we've done a lot of work on that. Again, I won't go through that in detail today. If you look at an additional loading cycle and go all the way up to 6%, then what you see is, of course, a lot more straining. Although it's still inhomogeneous, it still has a few areas where there's still slightly negative stresses. These are histograms of what the strain levels are, right? Although you start seeing kind of more of a saturation, but it's still quite inhomogeneous, as you can see from this distribution. What is more interesting is if we look at the difference between them, or the increment between 2 and 4%, and then 2 to 6%, if we look what happens between 4 and 6%. So essentially the difference between these. And what I'm going to show you now is not the difference between these, but it's actually the correlation between 4 and 6. So it is an experimental measurement in and of itself, and it's this. And what you see here is essentially almost identical to the response to the distribution that we obtained in the loading between 2 and 4%. So essentially what we see is that plastic deformation just keeps accumulating at the same places, which are essentially almost in some sense determined from the very beginning, just by the microstructure itself, really, right? That's kind of how this came about. Can we just use a microstructure to determine what will happen in the future, since this seems to be, at least in the mesoscale, what drives the development of the strain accumulation. So plastic strain just continues to pile up at the same place. Same thing for fatigue. And so here's similar kind of thing for fatigue. What is this? 1,000 cycles, 10,000 cycles, 30,000 cycles, and again you can kind of see. Well, first of all, the homogeneity obviously as expected, and then this increase in strain. How does that correlate to damage? However, right? Ultimately, that's really what we want to look at. So essentially, we did these type of experiments to study that. So this is all still with the Hastelloy X material. So we start with a, let's say, small number. Now we've done even smaller than this at this point, but in this slide it says 1,000 cycles, right? So we start with a smaller number of cycles before failure has actually occurred, and we would, and this is a DIC pattern, no cracks are observed here, we would obtain the strain field. And then add an additional 10,000, or I guess 9,000, that's wrong, so total is 10,000. So an additional 9,000 cycles, where now at 10,000 cycles, we actually see cracking that has occurred. This is an image at this point when the cycle, the 10,000 cycle is concluded, and then sometimes we do another half cycle just to open up the cracks so we could look at them better. This is an optical image. This is an SEM image. And what we do is we kind of put the two together. So this is a superposition of the strain field measured at 1,000 cycles before any cracking has appeared, and the cracks that appear at cycle 10,000. And again, here's the close-up of that one that I showed you that we also have these images from the SEM. And this is a very high resolution image, and I can zoom in, and it may not be exactly visible, especially with the lighting, but essentially almost every stress concentration here has a crack in it. Right? If I zoom up in here in the upper left-hand corner. So you see, well, let me point it out here, right? So almost every stress concentration has cracking associated with it, and even some of the smaller ones. So that was essentially an indication to us that indeed these areas of strain accumulation, which seem to be determined even from very early on in the fatigue loading, even from the very first few cycles, are the locations where failure would end up happening, right? So, but this is more than just a qualitative correlation. We also have we looked at quantitative correlations, and essentially we measured what we would define in some fashion as crack length, and we just do point to point rather than following the entire crack length. And we try and correlate that with the length of measured strain at 1,000 cycles. So this is a 10,000 cycle image. This is a 1,000 cycle strain field. And what you see here is whether you have, we have what we think of as transmitting boundaries. You can see here, for example, there is slip transmission across this grain, or blocking boundaries. Here, there's a grain boundary that blocks transmission. In either case, it doesn't matter. Whatever you have a certain length of strain concentration, you have following a crack. You have a crack following something. Now, I don't know exactly when between these two this happened, right, in what sequence, but all of these areas cracked. This is a histogram of the strain bands of various lengths, and this is the cracks of various lengths. So this is at 1,000 cycles, and this is at 10,000 cycles, right? So that seems to be a very good sort of indicator of, well, okay, here's where cracking will occur. Same idea in creep. Again, now different project, right? So kind of moving on to this DOE project that they were interested in this stainless steel 709, a particular steel that was of interest for these sodium fast reactors. And now they were interested more in creep and creep fatigue. So these are, again, macro scale results, what you would have as stress strain curves as a function of temperature, or creep compliance as a function of time. This blue line here would be at room temperature. This red line is at elevated temperature, at 650 C, which was the operating temperature. And the 250 versus 500 MPa are the same fraction of yield stress at that temperature, if you're wondering where those numbers came from. So, okay, what we would expect essentially from a macro scale, but what about micro scale? So do we get the same type of strain accumulation in creep, and do we get the same type and potentially at the same locations as we would in plasticity? So to investigate that, we kind of devised this protocol now differently. We do not have identical microstructures that we can test again and again, right? And once you test it plastically, that's it. So essentially what we did here is the following. We did one plastic cycle. This would be above yield, right? This is just stress. So this is above the yield stress. This is at 650 degrees C. So we did one cycle where we did plastic loading, followed by one creep loading cycle at the same stress level of a certain dwell time. Maybe we played with the dwell times and other things. That's, again, I won't go into those details. And what we see here is the correlation between, so this is the strain field. Again, this is all in tension. This is the dominant tensile direction. So it's a correlation between the strain field, the residual plastic strain field at this point, that's this image over here, with the plastic strain field at this point, which is this image over here, which essentially is the combination of the plastic cycle and the creep cycle. And if we look at the creep cycle only, that's this part here, which would be correlating this point with this point. And if you look at the first and the third image, they're again very, very close. So really creep essentially continued strain accumulation at the same point where plasticity had accumulated. Okay, now you can say, well, this is biased, right? Because we already loaded it plastically, so it already had deformed there. But I don't know how to do this without doing the sequential loading, right? So, but certainly the mechanism seems to be the same in the case of this sort of creep. Creep fatigue defined as adding a dwell time to the peak of the fatigue cycle. So one cycle now would look like this. Stress as a function of time would have a certain dwell time. And again, you can play with the dwell time, and that's an important parameter. So again, what this shows is evolution of the microscale strain field with dwell time. With the creep fatigue. So this is at the end of the first tensile cycle. This is at the end of the first compressive cycle. There's a lot of things you can study here, and some of the strain reversal and things like that. And again, that's what this project is about, but I won't go through that detail. What I'm interested in here more is the evolution with cycling. So this is essentially at the 8th cycle, tensile and compressive. And what you see, again, these are very similar. Right? So again, we see the strain just accumulating at the same locations as we saw before. This is at room temperature, same thing at high temperature. I won't stay with this too long. What about cracking? Well, same story as what we saw before. This is the strain field at 100 cycles now. Right? So this is at the end of the 100th tensile cycle. No cracks have appeared yet. This is at the end of the 400th cycle. Now we start seeing cracking. And we see, and again, it's not very visible here. If one zooms in and looks at it, some of these arrows are highlighting where their locations are. There are cracks that essentially occur at exactly the same locations that these arrows are highlighting the strain concentrations. So the same idea that we saw previously also happening in creep fatigue. So again, this kind of brought up this assumption, let's say, or this thought that the microstructure that we have will essentially already predetermine where cracks will occur. If this is the case, we should be able to predict that. And again, people have tried to do this and predict even these types of strain fields through deterministic approaches. And so most of our work is experimental. So we started looking at some of the machine learning as sort of a substitute to these more complicated models. We have done some of the deterministic modeling as well. It can be quite involved depending on what it is that one would want to do. So here the goal was to start with this experimental information of the microstructure and try and predict this information of the strain fields. Eventually, with potentially maybe some other continued sort of string of machine learning models, have something else that would also predict cracking. Like I said, a lot of people have tried to quantify this relation deterministically. So here we'll try and do it with a machine learning code, and we'll use what are called fully convolutional, fully connected neural networks, which really are same. And I'm not a machine learning expert by any stretch. So mainly what I've learned is through talking to people and reading things. But what I am interested in is what we can do with these, and in a robust way, right? That we can actually sort of defend, yes, this makes sense. So yes, it's some sort of elaborate fitting, but does it make sense in these particular situations? So essentially, we want to start by inputting grain texture from eBSD. We will do this. Now we'd like to do this experimentally. Well, you need very large numbers of experimental data. We don't have those numbers of experimental data. So we started out by saying, okay, let's look at this numerically. So we will generate artificial microstructures through Dream3D. The corresponding strain fields would be obtained not from DIC in the experimental case, but from crystal plasticity finite element simulations. And in this way, we can get sufficient numbers of training data sets that would be required. This leaves open the question of, well, how do we correlate with experiments, right? But anyway, let's put that aside for now. If we can achieve this, then this opens up other avenues beyond just simply determining failure. It opens up avenues of engineering the material, of course, right? Which nowadays, especially with additive manufacturing and so on, it becomes physically even more possible. So we can do also optimization in some sense. But really all I want to talk about today is this. Input orientations. So what we're going to use is actually rotation matrices, not Euler angles, right? So we would have rotation matrices. This would be 9 components. So we're going to input these 9 components into our network and extract 3 strain components. That's basically the idea, right? So this network here would have to extract the 3 strain components in very simple situation, just uniaxial tension. Loading matters, of course, as well, right? That's another issue, and I'll talk a little bit about that. Okay, well, let me skip that a little bit. So here's how we will do this. We will generate, as I said, a numerical microstructure now with Dream3D. This is what this 3D element is. We'll do this, however, all in 2D. So what we do is we take 2D slices of this microstructure, and we move the slices far enough away, at least one average grain size away, to get different microstructures. These grains are created from this log normal distribution here, and you can kind of see a typical slice here. And then we throw away the boundaries just to avoid any edge effects after the simulation, I mean, right? So the boundary conditions, the crystal plasticity simulation is always an open question. We use an FCC material. It's represented by this black stress strain curve here. And then I will show you later on, if we have time, some results with this red curve. And then we put this to crystal plasticity and we get the strains, and we generate 9,000 such samples, 8,000 for training and 1,000 for validation, right? So for each sample, we would have as an input, as I said, the rotation matrix, as an output, the strains. So here's the network that we use, or at least the one that we started with. There's some work in the literature on that already, and now even more so in the couple of years that we've been doing this. So we started with this network that we actually took from the literature. It's just a regular convolution neural network, sort of series of convolutions in an encoder and a decoder. And it actually produced pretty good results, and you'll see the results in a little bit, right? Again, as had been seen previously in the literature. But then we added at least what the student calls modern architectural components. These are modern architectural components, I don't know, 6-9 months ago. I don't know if they're modern anymore, right? Because this moves extremely quickly. But the components are the following, and we kind of did this ablation study to study each one of these separately. But this is, I think, where kind of the more of the interest comes in. The first and main thing that we did is we added these, what are called skip connections. These are represented by these gray lines here. And essentially what they do, again, to the extent that I understand, as I said, I'm not a machine learning expert, but this is exactly what I try to understand, what physically this does, right? So the way that I understand these skip connections, okay, so you have these series of convolutions, fine, that's a regular network. It essentially downsizes the image spatially while increasing it in depth, and then it reconstructs it kind of moving upwards. And essentially each set of convolutions here kind of acts on its own, which means that it has to learn not only whatever its own function is and whatever it's doing, but it has to learn all the stuff that, you know, the previous convolutions have learned. And you can do this all the way going down. What skip connection does is it helps this out by directly passing information from one convolution layer here to another. That's what this black box here is meant to be. So essentially each layer doesn't need to relearn everything that the previous layer had done. And that is extremely helpful, as you'll see in a little bit. So this is one modification. Another modification is what they call depthwise several convolution. The way that I understand this is that sort of an irregular convolution, which would be this sort of green image over here, you essentially optimize this for all inputs at the same time, whereas in the depthwise separable, you look at each input separately. Now you may say, well, okay, but isn't that a bad thing? Does that not mean that you're losing any sort of coupling that you would have between the channels? At least this was my first inclination with this. And the answer is maybe, but if there is sufficient information in the images that you're looking at, the strain field in this case, that establishes what the coupling is, it can still be picked up. And as you see in this case, it will work. We also added this, what is called the mobile bottleneck convolution. This, I don't understand exactly what this is. It's totally a numerical thing to accelerate. It only works for depthwise separable convolutions, but it accelerates this process, which otherwise can be very slow. I just think of it as a numerical tool. And the other thing that we use, which is actually quite interesting, is what is called the residual functions. Actually, the residual functions actually motivated the skip connections. They're the same thing. It's just happening at the convolution level, right? So essentially, for each particular convolution, instead of having whatever you're doing here, trying to learn, the whole thing, let's say f of x plus x, you furnish x directly, so it only needs to learn the residual of what is f of x, again, helping it along. So really, this is a sort of local version of the skip connections. So the skip connections that the residual are the ones that will provide the most detail. But what is the most interesting is when you combine them all together. Right? So after being convinced that, okay, these kind of make sense for us to use, we then went ahead and looked at how good they are. And the question is, what to use as a metric. And we looked at many, many metrics, and we have results for many of these metrics. But one interesting metric came from computer vision. And it's this one here, what they call the structural similarity index. It really is an imaging metric, right? Which essentially kind of gives you a sense of luminescence and contrast of the image and some of the structure or the patterns in the image and so on. And that actually works very well for what we're trying to do here, because luminescence can translate to mean strain. Contrast can translate to strain variation. And we actually indeed have these strain band patterns that develop, which really would be what the structure of the image would be. And this is the definition of the SSIM if you're interested in looking at it. But I'll show you some of the other metrics as well. But a lot of what we do is based on this SSIM. This seems to work pretty well. So here's a median result. This is a median result, right, from the whole data set. The three strain components, well, you can just concentrate on the dominant one, which is epsilon 2 in its uniaxial tension. So SSIM, best value is 1, right? So these are the 6 networks that I mentioned before. We can kind of just look at essentially the first and the last. This is the original, just the regular CNN here. And you can see these are the 8,000 training samples. It saturates at some point fairly quickly. And it's not bad. Okay, this is at, 85%, right? 0.85. But the complete network with all of these elements together is actually much, much better. And it produces much better results, even for smaller training sets. So let me skip some of these. Right. So why is this important? Because really what we're wanting to pick up is hotspots, right? Places where strain is maximum. And really, for me, this is kind of what convinced me that, yeah, this is a useful sort of path to follow. Looking at, again, what would be an average sample, this is the microstructure. This is the ground truth, let's say, which is the crystal plasticity result. And this is the prediction of the first and the 6th network, right? The one that combines everything together. And even the first network, as you can see, is not too bad, right? But if you look at these line scans, here is kind of where you will see the difference. This is strain as a function of that cross section, and all the dashed lines are grain boundaries here. And the ground truth is the black line, which is crystal plasticity. The original network, it's actually pretty good, better than anything I thought it would be initially going into this. But as you can see, it underpredicts some of the peaks, most of the peaks, actually. Whereas when you add the other elements, okay, it's not, again, right on, and you can see a distribution here of the error. But it's a significant improvement. And this is very important because it allows us to pick out hotspots, and that you can see here, right? So this is, this is what is called the DIC score. It's another image metric that we found kind of useful. But essentially what it does is it concentrates on certain locations of the image of what we consider hotspots. So that's above 90% of the strain field. This is, again, the ground truth. And then there's a significant improvement with these hotspots, which you can actually see here. This is the entire data set. This is everything. This is all 9,000 samples, all strain levels. And these bands are plus minus 2%. Thought of as, let's say, the error, the acceptable error, whatever. And as you can see, FCN1 underpredicts. These are the large strain values, whereas this one does a much, much better job with the hotspots. And really, that is kind of the main key thing. And then beyond that, and time is running out, but beyond that, we looked at now varying things, right? So what if we vary load? Can we predict other load situations? Well, it turns out that for that network that's already trained, we couldn't do that. Once strains started change, although you'd think, well, they always accumulate the same spot. Why not? Well, it didn't seem to work. What did work, however, well, is if we trained for a number of load points. So now we add one more input, which is load. So now you have 10. 9 rotation matrix components and load. And all the green points are trained, and they actually work very well. And then we started looking at, well, okay, can we interpolate between these? Yes, we can. It does a really good job of interpolating. Can we extrapolate? Not as good, although extrapolating to higher strains worked a little bit. You can see this in this sort of box and whisker plot, right? So the boxes are the 25 to 75 percentile. And there, again, this is the SSIM. It should be 1. It maintains pretty good values, even for extrapolated strains. Where it loses it is for smaller strains. Well, but that's where the thing becomes elastic. Right? This is crystal plasticity. Right? So that kind of makes sense. All right, so load. What about, I'll just run through these quickly. What about grain sizes? Grain distribution. Well, it's the same distribution, just changing grain size through this log normal distribution, either average grain size or changing the sigma, it kind of goes from uniform to bimodal. Again, extrapolation works a little bit. It works for smaller grain sizes pretty well. It was trained at 30. It works pretty well for 20 and 10. As you move to larger grain sizes, it started losing it. In part because you now no longer have RVEs when you're down to this type of grain size, right? So that is what we kind of identified as an issue. Can you play with the microstructure, right? So we created these microstructures that were sort of more additively manufactured type microstructures. It works pretty well when they're horizontal to the load. It doesn't work as well when they're vertical, right? And I think the reason for that is because you end up having certain grains that carry most of the load and the other ones don't do anything and you cannot pick that up. Again, let me skip through that. And now, and this will be the last thing to show. Transfer learning. Can we use this for a different material? And this is the way that we envision bringing experiments into this, right? Because experiments will have very limited number of data points, right? This is kind of the key thing. So can we use the existing network to predict a different response, let's say, this red stress strain curve? Now, it's still an FCC material. You could do transfer learning on different crystal structures. That's a bit more difficult. We've done a little bit of that. But so we create a new data set of 900 samples, 800 for training, 100 for validation. Different microstructures, I mean, same distribution, different microstructures, rerunning everything and so on. But with this curve now, right? If I just use the 800 to train this network, we get this, which is actually, again, not too bad. The average SSIM is 0.76, but it's not as good as what we had earlier. If we do no transfer learning, just take exactly the same network with those weights and biases, we get, even this gives us a pretty good result. If we do transfer learning with one sample of the new material, it's not very good. But that's because it's way overtrained. But if we do as little as 50, and then this goes up to 100 and 800, we actually get very good results. So transfer learning, at least within groups of the same material, seems to be possible to work pretty well. So for me, this is kind of an eye towards, well, if we can actually train something numerically and then sort of adjust for that with a small, not 50, for example, 50 experiments is doable, right? 50, maybe 100. 9,000, maybe not so much, right? So this sort of transfer learning seems to be a sort of a good scheme to be able to move in that particular direction. And basically, well, all right, so then after that is the inverse problem, which I'm not going to talk about at all, but the inverse problem is exactly the opposite, right? So you start from a strain field, which microstructure gave you that, and that actually seems to work pretty well with a very, very similar network. Not exactly the same, but very similar. But that's okay. Because of lack of time, I'll stop here. And I'd be happy to answer any questions.
Lovely talk. I think this is really interesting in seeing how some of the work that has historically happened experimentally can, the moment you mentioned 900 samples, I'm like, oh, wow, that's just brilliant. That sounds like, reminds me of the amount of effort that to polish all those samples back in the paper. The question I had was, there's two elements that used to plague a lot of the thinking back when everything had to be done experimentally, which is around strain rates and temperatures. I think the data that you showed initially, I may have missed that, but it was at a constant strain rate and at ambient temperatures, presumably.
Well, most of them were all of them were at a very slow strain rate, so they were not at the acoustic type levels, even at that level, right? But some of them were at elevated temperatures. I think I mentioned some were at 650. Some of them I showed were at 650 C. Most were at room temperature. We have a large set of data at high temperature as well. I just didn't want to go into too much detail on that, but I think from a modeling perspective point of view, that would be changing the stress strain curve. So it would probably be maybe even an easier job, actually. That's an interesting thought. We never pursued that. But it may be even easier because it really is the same material at a different temperature. But I think effectively it's just a different stress strain curve. So it's kind of what the last couple of slides that I mentioned.
Kind of specification. If there is a kilogram read cycles that could improve your performance or even sort of relieve some of the strain accumulation, will that be something to explore?
Possibly. I mean, so you're thinking more now in terms of the material design aspect. Yeah, yes, certainly, but I would be more comfortable doing that once I had a model that corresponded to reality. And this one doesn't yet because it hasn't been connected to the experiments. I mean, crystal plasticity in and of itself, okay, so you're training this thing on crystal plasticity. So you cannot expect it to be any better than crystal plasticity is in terms of predicting experiments. So really all this does is extremely fast crystal plasticity, right? So you can do crystal plasticity like this once you've trained the network. But the limitation is whatever limitation crystal plasticity has. So you need to work on that a little bit. And the way that we see that is by bringing in the experiments through this transfer learning. So essentially retraining now on real data, but something that hopefully is close enough to learn that. We haven't quite achieved that yet. So the other thing that we're looking at is sort of doing this transfer learning on a residual, kind of looking at, this is all kind of ongoing, right? I'm just throwing out ideas here, but this is the idea that we're pursuing. So looking at the difference between crystal plasticity and experiment, and that residual tells you what crystal plasticity got wrong, and then you form something that you will train on what it got wrong so that next time it doesn't get it wrong, right? So that's kind of the line that we're pursuing. Once you have that, then I think you can start envisioning design.
And presumably you can work with even a different loading.
Yes, well, we've done biaxial as well. I didn't talk about that. That was one of the original criticisms when we first published this was, oh, this is only uniaxial. So then we added biaxial. So yes, that's doable. You could always, you can have something that's as complicated as you like, and you can always retrain it for that. But the whole point is not to have to do that all the time. And yeah, that's why we're focusing more on the transfer learning. Or thinking. Yeah.
Yeah, I think there was two elements to it. One is at the moment you've got the ground truth. That's really what we're doing. Back to having around. I think you then answered part of my question because you said, well, these can run it's a magnitude faster than running the CP. It wasn't quite there. I've got two questions. One, so what? So you can run it a lot faster. What are you going to do? What are you going to do now? And the second one is when you put it up right at the start, you talk about things like you were talking about sodium reactors, multi-axial stress states, not biaxial, multi-axial. That's uniaxial.
Right.
So how are you looking at translating that into so two questions really. One is an engineering loading environment. How are you tackling that multi-dimensional problem? And the second one is, what are you doing with this information?
Right.
So it's not just an academic, where's the engineering application?
Right. Well, yeah, like I said, at this point, essentially what you have is a fast crystal plasticity simulation. And, as you said, okay, what would you do with that, right? I mean, unless you want to do some optimization or whatever else with crystal plasticity, but translating into reality is exactly what I was mentioning earlier, right? So I personally need to do that extra step, then it becomes a useful tool. So that is clearly, well, for example, you could do microstructure design if you wanted to, right? That would also be possible. You could do that. Right, and you could do that. People have done that again also with deterministic modeling, right? So you could just do Monte Carlo type simulations and so on. I think in terms of, but again, same thing, depends on what you do the simulations with. There's people that have done probabilistic modeling with crystal plasticity. But how good are those results if they don't translate to, if they don't agree with experiments, right? So.
Yeah.
Yes. Yes, I agree.
Amazing work. Is the pre-trained network going to be made available for potential use with more data, in brackets, more experiments, or shared as an open source model?
Yeah, good question. I haven't thought about it. I think it could be. I think it would be, I mean, we just talked about 2 or 3 things here, right? So loading, for example, biaxial, triaxial, it doesn't do all that. So I think it will become, it's almost obsolete even with what we've done now, right? This is what, 6 months ago. So yes, but it will be continuously changing. So, really the best thing would be to have someone curate these things, and also as they change, and that we don't have the personnel to do. But that's a good idea. I'll look into it. Yeah. I mean, I'm not the sole person involved here.
I
But
guess people.
yes,
And as you say,
sure.
you add circumstance, maybe the model becomes wiser.
Sure. It's a very good idea. I'm personally totally open to that. I think that's a very, very good point, right? I haven't thought it through, but yeah, sure. They could email me for more details, right? So yeah, absolutely. I mean, at a minimum, we could share with whoever is interested, right? But then, put on GitHub or something. That's also possible.
I think it's also useful to have, if you've got 9,000 training data, it can be useful for trying different neural network models to see which ones are the more.
That's also possible, putting the data up there. Yeah, that's also possible. We did contact a few other folks to try and get some other data from other people,
Yes.
but that's kind of the reverse, right? So I'm open to that.
So this one is very interesting. So my question is, do you think it's necessary or sure method to extend this to the interest?
Yes. Yes, that is also one thing that we are currently working on. It's also one of the main issues that we've had, well, it kind of was driven, again, my own background is from the experimental side, right? It kind of was driven from the experimental side. We have this 2D DIC. One question that always comes up is, well, this is 2D, what happens in 3D? Not even what happens necessarily in 3D in the sense of sort of deep inside the material. That's something different. But to what extent does the underlying microstructure right below the surface affect what you see in the surface? So we see these EBSD things, right? That you see this little tiny grain, but below it, there could be this enormous thing, or it could be something that has slip planes that are pointing directly out, and then everything will come out this way. And so, that's always been an issue, right? So to what extent is it involved here as well? So we have the Dream 3D because we have the entire microstructure. So essentially what we do is we are doing similar things with increasing this volume and now doing this in 3D. So far what we've seen, and there's a couple of studies that have already looked at this, right? And we're getting sort of similar results. As a starting point, okay, just for the surface effect now, right? Rather than the full 3D. Although if you go to triaxiality, the full 3D is important, but I'm thinking, Saint Venant effect, 4 or 5 grain boundaries, grain sizes inside won't matter anymore. So you could just think of that all as a sort of homogeneous. Well, it turns out it's closer to 2. Maybe after a couple of grains, maybe 3. Now you can kind of think of this as homogeneous, right? What we're trying to do now, so yes, these are all very good questions, right? So one thing that is currently sort of also on the way is, can we predict those 2-3 grains from what we see on the surface? Can we do it from this? Would we need additional information? Let's say 3D DIC, where you have an outer plane displacement. Is that going to allow you to predict this sort of, iceberg effect? That's kind of how I think about it, of the underlying microstructure. Now, if you move the whole volume, things like triaxiality, right? This would drive internal defects to cause failure. Yeah, these are all open questions. Well, I wouldn't say a lot, but there are, right? So yeah, I mean, we've done a lot of volume correlation as well in various materials, but we haven't done in metals, although they do exist. You could do, through X-rays or neutrons, you could find, you were doing some of these, right? So you could get that. Getting internal microstructures a little bit more difficult, but that's possible. We did that at Argonne once, right? So with some of these near field X-ray diffraction things, but I would not say a lot. In fact, very little. So can you again translate to training a model? Not yet.
mean, obviously you can use an X-ray to do 3D mapping of the grains, as you
Yeah.
said.
Yes.
But again, you're not going to do 800 samples.
No.
But I do worry. I mean, I think Mahmood's work, David wants to comment on that, as he's looked a little bit at the difference between 2D and 3D. And I do worry that, we spend all our time doing DIC in a microscope, looking at the surface. You said it's only only the top two, but even the top two are important because we only see the top one.
Yes. Yes.
So
Right.
we may be spending our time chasing our tail.
Right. Right. Which is why we're trying to do this inverse problem of extracting. I mean, if that works, first of all, I didn't think it would work on the surface, and it seemed to have. But if the inverse problem works in the, 1 or 2 layers in the interior, that would be a very powerful result. But I don't know if it will. It seems like a highly overdetermined problem, right?
Yeah.
Hang on, a book. Reality based. Permanent based. I have one which I thought about, I just thought about as you were putting it up, because you presented strain controlled
Right.
tests. I was just not thinking in my head with feedback. So if you had a heavily textured material, obviously it would respond very differently to it in a stress situation.
Right.
Then you've got really interesting feedback, haven't you? Because the microstructure would affect the amount of macroscopic strain you can apply, which would affect the microscopic strain. So there's also how this feeds back into materials constituent models.
Yes.
That's something I wouldn't mind.
Yeah, and I think that is the reason why when we did this texture that was highly elongated, it behaved very differently when it was perpendicular to the load versus parallel to the load, right? And the load here being strain controlled, right? So.
So, yeah, general discussion points on that. Which one? What stops us from getting to that level of coaxial states being used? Is it computational power? Is that the limitation? I've had a similar conversation with subsurface folks who argue that go talked about scale model. Is it computational power that barrier? This is just available for all of.
I think you should ask.
But no, I have the microphone. No, I can say something, but yeah. Well, not computational power in the sense, at least that I would think about it, right? So let's say for crystal plasticity, right? And if you say, well, I want to do, ab initio calculations or molecular dynamics or whatever, then okay, fine. Yes, we don't have computational power to model every molecule, every atom in the universe. But if you say, well, something like, we have a finite element framework, something like that. No, I don't think computational power is there. The question is the models themselves, right? I mean, again, let's go back to crystal plasticity, like you said. It's been around for a few decades, but it doesn't quite. It's nice. It's very nice. It produces, very nice pictures. It has some semblance of reality, right? And it does seem to agree on some things, but it's not something that works on everything. It doesn't incorporate grain boundaries. So then people do a lot of things to try and put on stuff in grain boundaries. We've done a lot of work with grain boundaries, right? Trying to come up with, from molecular dynamics, for example, energy barriers or grain boundaries, and introduce that as an additional element for failure. The boundary conditions are always an issue, right? So that's why we cut out the frame around it. So I think it's kind of more fundamental. I wouldn't say understanding necessarily, because the physical understanding, it's kind of like fatigue in some sense, right? So the physical understanding of fatigue, we've known what causes fatigue for, a couple of 100 years. But to say that this particular thing, this particular component is going to fail at this point on this exact cycle, that is still not there. Kind of like that's perhaps an extreme condition. But anyway, that's my response. So I don't know. Yeah, well, another way of putting it.
Well, I think we've just not got the balance right in terms of as we're moving on our understanding, because we need this, I mean, the neural networks, my view is they're a great way of capturing all this information in quite a pragmatic way, but actually our models aren't as good as we think they are when they come to some of the detailed predictions.
I guess the other point is I guess the other point, you've done some of this, and maybe that's also one of the applications of your work, John, is that one of the things that is, as you mentioned very briefly, it takes very much less time to run your neural network than it does to run a CPFE model. So, you know, if we are going to go up in scale, one of the ways is through this what they call surrogate modeling, and I know BIS have done lots of that, and maybe that's a way in which you can move up the scale. Your models aren't any better because they're only as good as the scale you've started at, but at least they give you the wrong answer more quickly on a larger volume.
After training though, right? So the longest time is running the 9,000 CP simulations. The second longest is the training, and the third almost is extremely fast is the running. I am basing my hopes on transfer learning. It has not been shut down yet. I thought it was, you know, sort of like a pipe dream random thing, but it does seem to work in some cases. So I'm really basing my hopes on that in terms of connecting it, you know, to reality. Yes, I like that a lot. Yes. Right. Yeah, you know, I like that idea. Yeah. That too. Yes. Well,
I'd just like to say thank you again to John. Thank you all.
Thank you.
John, I'm going to say class job and voice and ICAM. Thank you, Amanda and Tracy and everyone setting up today. And thank you everyone who's been online. If you've been online, please fill in the feedback form. That would be really appreciated. I'm sorry you can't join us for a snack and John has been chair of the Society of Experimental Mechanics in the US, which is also a very important organisation. You're a young researcher. You know, I've been to a number of their conferences, and I've published them, so I was published in their journals, and they are a really important organisation. So do take a look on their website as well, because that's a really interesting. Anyway,
definitely.
To finish, just to say thank you to John again.
Thank you. Thanks.